Okay, so this is something we got to use a lot last semester because of limited lab capacity. I had to broadcast from this lab to that lab, and we had 2 half labs. Sounds like I'm a dog breeder. Yeah, we had 2 half labs in here. Different type. It was half capacity lab, so 12 students here and next door. This will give us a nice close view that you can use to review the viscosity during the pour and that sort of thing. So I'm going to get my lab coat and I'll be right back.
Mikey, I see you running over there.
Yeah. Yeah. But only Brian's like 3 days now.
Does it do like your next class?
No, it's personal project that I'm trying to get through.
Huh.
Actually, for my honors contract, so I'm trying to get it so I can show it to them so they can do a demonstration of what I'm working on.
Yeah. I never did it either. And I just said that's part of my tuition. Yeah. Yeah, just kidding, stats. Yeah. Well, I want you to come with oh. So that's I take an old one. Yeah, that. Do it for video. Alright, you can always tell who's in charge when I put this thing on. Okay, who's ready? So we can go ahead and take our stations then, and we will begin. So it's like something off some science fiction movie, I know, especially with the mask and a magma man. Okay, so let's talk about the first batch. First batch we're calling is L1. And so it is a white sand, sodium carbonate, calcium carbonate with a little bit of limestone, and 0.02 load of cobalt oxide. So that should be a fairly standard cobalt glass. So we can go ahead and come up here, those that have volunteered. So the stamp will need to get ready with a L1, and go ahead and practice the torch. Feel free to get the feel of the counterweight on the door. Just kind of lift up and feel the general weight of it. Alright, so the zigzag pattern generally here like this as we unload the furnace. Yep, that's right. And it's alphabetical at that point. So get where you can see the glass, or you can move up a bit, but I will need a little bit of a zone here so we can move around. And so the best place to stamp is probably to stamp back here, because I'm going to be swinging around with the hot crucibles, and as it's cooling down, you can typically step up and stamp from the side. One thing to keep in mind with the torch, try to keep the torch as much as possible off the previous poured glass. And so you'll have to be a little creative with the angles, because we're going to grid it in like this, and then maybe a few others back here. So you'll have to just generally try to keep that in mind. Okay, so the first glass, cobalt glass, L1. happen for a while. So okay, so now fire polish the spot that's left. Make that cool down in. Okay, that's good. Now hold on a second. Right about there would be about right. It's gonna be hot, so that's your finger. That's good. So that's a pretty typical pour. Did it get you?
Oh, definitely.
Kind of feels a little toasty.
A little bit.
So the dark pigmented, the dark glass sometimes is a little heavier on the radiant heat. If that gets to be too much, you can kind of go to the end of the stamp, or you can put on a nitrile glove. Does help.
Yeah, I was thinking about that.
So those are over here. It's pretty toasty. So this is a really nice dark blue glass. So this was a full load of the Cobalt 0.02. And so some of you maybe are glass collectors or have people in your family that collect blue glass, so this will look familiar. Okay, so that was L1. Next up is M1. What's that? Right, that's just to knock down the radiant heat. I do have red thermal gloves, but maybe try that, see if that's enough. We could then move to the...
We got like a full rolling one in there.
What are those ones?
With those, it's hard to hold the
Yeah.
stamp.
I was thinking like work gloves. Something like that.
So I do have some welding gloves.
Oh,
Yeah,
that'd be perfect.
That's perfect, yeah.
That's exactly what I was thinking of.
Thanks for
I
letting
have
us
some
use
at home. I
those.
would have brought them.
Yeah,
I would have known about this.
and should have gotten volunteers report. All right, this next one, M1, is the U.S. Pigment Purified Silica, washing soda, calcium carbonate, cobalt, and sodium sulfate. It's going to be pretty similar, but with the addition of sodium sulfate. So we'll be able to compare with these two glasses the role of the sodium sulfate. Will it make a big difference in the amount of bubbles? This one looks pretty clean inside, so we'll see. So next up, sodium sulfate. Now as we're pouring, watch for subtle differences in viscosity. So how thick the liquid looks as it's being poured. A low viscosity spreads out a lot, a high viscosity spreads out not as much. You'll also hear what's called crazing. What you're hearing is little cracks forming in the glass because it shrinks at a different rate than the ceramic. So shortly you'll hear lots of that going on as we get more and more crucibles. But that little sound, every time you hear that, there's a new crack that's forming in the interior glass. So anyway, so we'll pour the next one right there. So M1, yes? This does not look like cobalt glass to me for some reason, so we'll have to see what's going on there. Okay, I think that looks good. Probably didn't have to be quite that deep, but that's good. It's fine. I'm just saying this, that it probably didn't have to be quite that much. Now, you will notice some fiberglass. Resist the urge to touch fiberglass. We have had, not under my watch, but previously there were some people that were playing with fiberglass, and it surprisingly it bends. But the problem with this is it's not like thin fiberglass that you might have for insulation. It's thick. So you bend it and you're like, hey, it bends. And then all of a sudden it snaps, goes straight, and sticks directly into your skin, kind of like a nail gun. But it can leave little chunks of glass in your finger, which is bad. So resist the urge. It's a powerful urge too. You're like, ooh, look at this, but it gets you. I've been stuck by it before as well. Okay, so this is cobalt glass, but I think the loading might be different than what's listed. So let me just verify that. This says 0.02, and the previous one says 0.02. So I think it might be down by another decimal. I think it might be 0.02 and 0.002. Because this looks typical for O2, this looks like it's about a tenth less. So I think there might be a discrepancy on the record, but I think we can figure it out. But I think that's what's going on there, because it does look a lot lighter. So no big deal, just trying to sort things out as we go. All right, next up, we've got N1. This is, I guess, mostly Fisher Purified Silica with some white sand and some Mason sand. So this is a mix of silica source. That Mason sand has iron in it that will make the glass turn a little bit greenish in color. We then have sodium carbonate washing soda, crushed limestone as our calcium source, more iron, plus 0.4 grams of copper oxide. So this will have probably some blue plus some greenish tint from the iron. That's what we're expecting. So we'll put that one right here.
Is it N1?
This is N1. N1. All right, so going from the middle. Okay, I think it's good. And one of the things that we often see with the copper glass is the flame has some excess carbon monoxide, and I can see it already forming there. The copper, some of the copper gets reduced in the surface layer of the glass, and so the cool thing about that is there will be a copper mirror-like appearance, and so you'll be able to see that kind of banding in on the surface of the glass. And I'll clean up these crucibles later, so we could, in theory, pick them off. I kind of chip off that glass so it's not like a bee stinger that's going to get you. But yeah, this is kind of cool. I can see, and you'll be able to see later, there's a mottled, coppery, like bands of sort of metallic looking copper on top, and that's due to carbon monoxide in the flame before it completely combusts. Has pulled some oxygen out of the oxide, leaving this copper appearance on top of the glass. So that's kind of neat. Okay, so let's see what's next here. So next up we've got O1. That is a purified silica Mason sand. Our first example of the borate. This is a half. The maximum for that ingredient is to 10. We've got 5 grams of borate. The borate melts first and helps lower the overall melt point. So be watching for a lower viscosity glass and a larger disc as a result. So far these have been kind of similar. These are a little bit smaller than the first one, but this one I'm expecting it to be a bit larger. So this also has sodium carbonate, calcium carbonate, standard pure stuff. And this one also has cobalt as the colorant. So we've got cobalt 0.2, 102 grams, but we'll be able to compare the effect of the borate between this one and this one. They should look almost the same, except for that. So 01. All right, going from the left. Borate sometimes has a little puff of smoke too, I've seen. Gloves are working well for you?
Oh, these are perfect for it.
Yeah. You haven't lost the dexterity and you get the coverage you need, so that's good. Alright, so there's some interesting effects that happen while glass cools. And that is, they call it the temperature at which the final color strikes. They call it the striking temperature of the glass. Sometimes the color won't pop in until it seems like it's cooled down quite a bit. And the color darkens. The reason for that is the metal sits in the middle of 4 to 6 oxygen atoms. And to begin with, the oxygens are moving so quickly they haven't formed coordinated bonds with the metal. But after it cools down enough of those bonds form that the cobalt's in its final like placement, and that makes that color more permanent. Now, again, I don't know what's going on with the color. I wouldn't have guessed that to be cobalt glass. I'm sure I'm not reading this wrong. Cobalt oxide, 0.02 grams. So the Mason sand would give us that green color, but I'm wondering if this is less cobalt on top of the iron color. I don't know what's going on. This is the typical 0.02 cobalt. This one says 0.02. This says cobalt dioxide. You've got manganese dioxide. That should be more purple. So there's a shroud of mystery growing on some of the colors. So maybe we can decipher this afterward. Maybe take a look at the ingredients back there and we'll try to verify what was added to these. After we do that, I'll make a copy of our batch records so that I can post it for people to look at the batch recipes, and then you can pick these up after I scan them. But let's verify the ingredients as best we can, and then scan it, and then we will let you take these to include in your report. Okay, so next up is P1, and that one this is the new one. I'm looking forward to this all week. This is the first time we've tried sulfur carbon, which is supposed to be brownish yellow. I'm excited. So we'll see. To try that color out, we tried a really high purity batch. So this is the Fisher Purified Silica, the reagent grade sodium carbonate, and the reagent grade calcium carbonate, plus 0.16 grams of sulfur and 0.5 grams of carbon, and some sodium sulfate to knock down some bubbles. These are pretty clean so far. Few little bubbles, not a lot of bubbles. We'll put this one right here, and we're hoping for brown, yellow spectrum glass there. P1. Pulling from the right. Restrike that, it's pointed out on the glass. There you go. Ironically, I see more bubbles than the one that's supposed to have the bubble reducer. So, I don't know. Maybe try angling it a little more toward me. There you go. That's good. hit that string, try to get that to go down in. Oh no, the pancake. Okay, go ahead and catastrophe. Stop a second. It's the first time this has happened. Oh! Go ahead and hit some more with the flame. Okay, we got that. I don't know, it was the one I wanted to see too. So, go ahead and stamp that. If I can time it right, we might be able to separate it a bit.
I'll wait a little long and stamp.
It's like Siamese twins.
I don't think we'll have any problem. You have a giant crucible
Yeah,
on there.
Yeah,
With
I
P1.
think,
You don't need
we
this
won't
little
have a
stamp.
hard time identifying that one. These things do happen sometimes, but not usually like this. So I'm going to try
Why
to
would you think that?
break that off. And if I can time it right, I might be able to rock this loose.
Maybe hold the glass down with that like
Yeah,
screwdriver
that's
that
what
comes
I'm going after here. So once I get this to come apart, I hit it with that torch a bit. Try it anyway. Not quite yet.
in. Yes. You say it hit.
We're making this up as we go here. You want to come off of the crucible.
Somebody stuck to the end of the channel last.
Oh yeah, that'd be hilarious. It's like the guy that super glues his fingers together. And then he glues it to his eye.
Oh.
Okay.
Wrench will make a nice little stamp too.
Yeah.
Throw it back in the furnace.
Good.
Gonna have to get a big crucible and put everything.
It'd be ugly.
Trying to get out the hammer.
Okay. Maybe we'll just let
They
that-
got two now.
Maybe we'll just let this be.
I mean, it
You
came
won't
off.
move that.
It came off.
Yeah, it snapped in half.
Just told us you don't like our drill.
Anyone asked you, Ruth?
Well, no, it was my fault, really, right? So, what happened there? I stopped a moment and I was talking about something.
You told them to move the angle of the torch, and
I
then
looked away.
Then you just dumped it.
yeah,
I looked away as I was moving and the bottom touched the glass.
yeah.
Okay, so normally Dr. Ray has laser focus on this, and so I will pay closer attention to the next one. Never had one do that before. So.
Colby, try not to do that to ours.
All right, so good news is, as long as it doesn't crack more, we'll be able to get our diameter measurement. Actually, let's go ahead and do a diameter measurement now. Sometimes when there's an exception like that on the glass, it can break further. Since this is already cracked, it's probably not going to crack further. But this one is, let's call it 73 millimeter diameter. 73. That was
P1.
No, P1. P1. Now, ironically, I'm not really seeing color. Yeah. So I don't know if if we burnt all that out overnight, because sulfur and carbon can get burnt out. So maybe this is too long of a batch. Supposedly this was like a fail-proof. This is how they color beer bottle type coloration, but no, I don't think so. So, okay, so moving on, Q1. This one, Fisher Purified Silica, Mason sand, majority Mason sand, 55 to 34 grams. So this will have a iron color, sodium carbonate, crushed limestone, iron oxide. So this is going to be lots of iron. And so that produces a kind of a greenish tint glass. and try to get any little shards out of the way there so it won't affect the next piece. Catch the paper on fire. It probably would too. It's hot enough, it might. Hey, why not? So, anyway, Q1 pulling from the middle, iron-rich glass. Ooh. Hit that bubble there. And this looks like it has borate in it to me. Okay, that's probably pretty good.
Your call.
Okay,
Yeah,
so the P1, and we're going to put that into a crucible because I think the heat's going to continue making that try to crack on us. So we'll put the pieces in here so it doesn't get thermally shocked anymore than it already has. And we'll set those up once everything cools down. Now that one has the color I kind of expected from the
There you go.
sulfur and carbon. So, I don't know, Dr. Ray's confused. So that one, iron can
We
make
did
this
the
color, but normally,
the wrong ingredient.
Have you seen one that's normally that?
yeah, the first one was like right in line, but the rest of them I'm like up here tap dancing like, hey, this is different. So,
That one.
this one, oh wait.
This is the wrong class.
If you flip it around, it might help.
No, you guys look familiar. So the Gerstley borate does have this ghostly 89.92, which certainly that wouldn't be. Okay, 19.37 of the borate.
Yeah, we had to do. We were doing the math super weird, but if you put the other side, it's going to have the actual like amounts of everything.
Hey. Okay, so this has 34 grams of the silica, 26 grams of mason sand, 13 grams of granucil, 19 grams of the borate. That makes more sense.
Yeah, we didn't hit tear on accident after we did the
I
first thing,
see.
so
So
we
this
we're
is
adding
actually,
it up. And
this is a double loading of the borate, which is why when I poured it out, I'm like, holy cow, what's happening? So it really spread out, which is kind of cool because now we see what a really low viscosity glass looks like. That one really spread, and that got my attention on, hey, what's going on here?
Gotta snap it back into focus.
Yeah.
It's a good thing we got rid of the other one though.
Right.
Touching.
So I think we're good now. So that makes more sense. We consider that it has extra borate. Borate makes it melt easier. So the Gerstley borate mineral. All right, R1. Is this one yours? Okay, this one's gonna be perfect. So
I'm gonna agree with that.
this is U.S. Pigment Purified Silica 46. It's about 50-50 pure to mason sand, sodium carbonate washing soda, calcium carbonate, a 2-gram load of iron oxide, and a 0.95 sodium sulfate. So this, I think, is going to be perfect. Perfect. Yeah. This should be the opposite to this one. So this will be a iron glass, but without the boring. And so that's actually a good comparison that we'll be able to compare those to see the effect of the boring.
You
So
can pretend that was planned.
it always
Yeah.
works out, you know, one way or another. So yeah, so that'll be a good control to compare those two. R1. Okay, so we will pour
So
this
strategic, we
one
didn't even know was happening.
here.
Natural.
And then one from the middle? Yep, to the left.
Or left. Sorry.
Feels really nice.
You need to strike away from the glass. There you go. You hit that bubble on the side to make that pop. And then you just keep working it. Okay. That's probably good. So the glass today has more personality than the stuff did on Tuesday. So you guys should be proud. That bubble, the problem with the bubble is it can destabilize the surface of the glass. And so that one might crack.
So like you said, perfect.
Perfect.
So close.
But the good news is it might not. But
Not a betting man.
so we will have to wait and see.
Yeah.
The color though, starting off pretty brown. We'll see if that ends up similar tint. It actually looks like it's starting to match up.
Yeah, they do look very similar.
Yeah.
I thought they were about like that.
Yeah. So
That's a liney for sure. Yeah. That's a liney color.
Oh
I
yeah.
was hoping you guys would work again today.
in some of the questions,
Yeah.
we'll be able to
It's
see
still sitting. I haven't done washing.
what's
yet.
going
I'm
on with
aware
the
every
surface
Thursday
tension.
now.
The tension of the glass sometimes can cause it to be very
Next time I order
hard,
my line, I go this
but
way.
then when it shatters, it'll shatter like safety glass into little pieces.
We're gonna work late one day.
So-
just to fix it.
Hopefully there's no shatter.
There might not be. That bubble's down under the
As long as it's
surface,
not
is
cool.
why it didn't pop. So it might be okay,
Lose all respect.
but it might. We'll see.
Oh,
So
Sam Adams one.
put the next one right there. Composition S1. This one is mostly purified silica, some whites, a little bit of white sand, 10 grams to 80 grams. Sodium carbonate, washing soda, calcium carbonate, dolomite. First example of dolomite. That's a calcium magnesium. We've got 0.2 gram loading of chrome oxide. This should be green. Kind of the 7-Up bottle green, at least it usually is. And 1 gram of sodium sulfate. Chrome is the best example of a 2-color coolant. It starts off dark brown and then hits about 600 degrees and then fades to green and then goes to bright green. So watch carefully as it cools because this one will change color halfway through the cooling. And right now this metal is several hundred degrees. It hurts almost immediately to touch it. So we'll put that one right here.
Ready for the next?
S1, yes.
Serious issue for the pork operator.
Need back up and there you go. that pulled in mostly. Looks good. Alright, so when we're watching the glass, just kind of, you can see on the thinner glass here, it'll have that brown to green change. It's kind of subtle. It's alright. It just needs to cool off a little more. Don't do it! I was walking across a parking lot once at a rest stop, and there was a quarter on the ground, but it was tails up. And as I went to pick it up, there was this voice, "Don't do it!" And there was this trucker way over there who was apparently watching that quarter. So when I said don't do it, it reminded me of that guy. Don't do it! Tails! Don't do it! It'll burn your skin off! I don't know, that was something. So anyway,
So did he pick it up?
I did. Which is probably why that crucible had that problem. Well, this is like 15 years
Finally
ago.
coming back to
So,
bite you.
15 years ago, finally caught up with me today. So I don't know.
Still paying for it.
Still paying for it. That's before I worked at Stout. So arguably, Stout was, I don't know. So we'll see.
Uh-oh.
Oh, it's probably the students that like that.
Huh. Well, that looks just like the iron glass.
Yeah.
Well, we'll wait and see.
Are you sure you have the right class?
That's right, class.
Just sheet.
They all have ones on them.
Yeah.
I guess we'll have to wait and see what the final color looks like, but that one does not say chrome to me. You guys were reading the bottles, right, when you were measuring this stuff out? It's like the Swedish chef. And, oh, the chicken! You go in the chicken. We'll see. Hopefully, it will turn green. Good. So, it says chrome oxide, so. Yeah, it does. So we're probably okay. We'll see if that gets to be darker.
Oh no,
Wait, uranium. Yeah. Okay, T1. This is 80 grams purified Fisher silica, 10 grams silica sand, 10 grams with a line through it.
Was that half 10 grams or something?
Okay, it was going to be sandbox sand, but then they changed their mind and went with white sand.
Big mistake.
Okay. So 50 grams sodium carbonate, 25 calcium carbonate. So actually a pretty high purity batch. And on top of that, we put 0.1 gram chrome oxide and 0.1 gram manganese. So this will be green and purple. Green and purple. This is finally turning dark enough green that I'm thinking this is chrome. It's a little lighter, but it is different. So good job on that. Okay, so this will add a purple tint to the previous one, essentially. So we'll put that one right there. All right, so center, T1. Nice and slow, quick. My gloves are smoking. What's your crucibles over there? They're so hot. Their promote mine is thinking like they're doing the aftermath. They're like the crucible heated up the propane tank, and unknowingly, so I think we're good.
That was supposed to be green and purple?
This is a chrome manganese. So the traditional color change that should happen is it'll be brown to begin with from the chrome, and then it should lighten up to be green, and then the purple should be kind of like they're all along. So now I feel a lot better about that chrome. This is what chrome's supposed to look like. So
Perfect on the wrong one.
Yeah, that's exactly.
so this
This one seems to have a lot of bubbles for higher purity.
I don't know. There was more bubbles on this one.
So if
So
we use a different form of light, it would show different color, like infrared light. It's the wavelength.
some glasses are quite different in ultraviolet or infrared. We could bring in an ultraviolet, but I don't think many of these have a lot of fluorescence. There are some glasses that we've used in the past using terbium and europium that are actually pretty bright fluorescent. So this is doing the color change that's brown right now, but I think that will eventually be bright.
Yeah.
I don't know. It could actually be brown from the manganese. So we will see. I think the color will change. It should say. It will become less dark and probably more of a lighter brownish green, maybe. Hello.
Getting a lot of that. I don't know. Maybe. Might.
You guys are opening up the uncertainty because
We're special.
they're special, yeah. So one here, and then the next one will be further back. So we'll just kind of line those on across. We open up a little more real estate in the back here. Real estate.
Why don't you just set the crucibles on that cart to begin with?
When they're glowing hot like that, it is a little too much for the pad. It's not like gonna blow a hole through, but it'll smoke a little bit. So I try to let it bleed off most of the heat onto the metal first. So kind of a staged process. Heat management. I think this is lightening up a little bit. Maybe it's just your shirt that's reflecting on it. So we'll put the next one here, and that is U1. This is sandbox sand, sodium carbonate, calcium carbonate, and a heavy load of copper oxide. So this one will be even darker, I think, than here. And so watch for more of that copper mirror effect once we get rolling. But a little bit of iron from the sand, clay box sand on top of the copper oxide. So this is U1, one from the left. Next to last. Okay, I see some copper mirror going there. And then our last one, I'll have to scoot over the camera a little bit to capture the full glory. Yeah, that one definitely has the copper effect. Look at that. It's kind of a ring. Great. This one looks like it's going to have higher iron from the clay box sand than this one does. Again, it's not at this final temperature yet. Yeah, we could literally cook marshmallows on this. Yeah. All right. So one more. We'll put that one there.
How is this kept hot just by the hot glass being on there?
What's that?
How is this kept hot? The heat just holds it?
So the heat from the crucible bleeds into the iron, and so then it makes the whole system have to cool down because I keep adding more heat to this plate versus this one. This plate still, I'm sure, is, yeah, this is still, what, this is in between 1 and 200 degrees. I should bring my infrared under here.
So we can just cook pancakes on it.
We could.
They're already making
I did
pancakes.
show this once. I put a drop of water on it, but it spattered, and a little drop of water hit on a piece of glass, and it shattered. So
That sounds kinda cool.
I don't do that anymore.
No one wants water, we want pancakes.
Yeah. With an extra little crunch because of the little piece of glass in it. It's like, oh, Dr. Ray's pancake. So this last one is another example of borate. We've got 9 grams of 9.8 of borate, 80 grams of purified silica. So we would predict, just a prediction, that it would be somewhere in between this one and this one in size, because this was a double load of borate, and so it'll hopefully be a progression between those. So we'll put that here. After we get all the batch records maybe corrected or finalized or whatever, you can look back through the data on the video and the data on your millimeter diameters and try to, make sense of the trends that we find, which I think they are here. So right here. So then this has a manganese dioxide, sodium carbonate plus washing soda, which is just really still pure sodium carbonate. It's just sold as a laundry booster. Crushed limestone, a little bit of iron from that, but this is 0.2 gram manganese dioxide. So this one will be more traditional purple. So it should be lighter than this one because the chrome tilted that one towards brown. But there'll be a slight yellow from the iron plus the manganese, but this one I'm expecting to be purple and a little bigger than this one, or a little smaller than this one, bigger than this one. Maybe. So, V1, last but not least. I'm trying to predict them so you have faith in science, but it's being a bit of a challenge this time.
You're not improving our base of science.
Yeah, so far. Okay, hit that bubble. Try to get that to go away. And that's probably going to persist, so maybe switch to the...
Got it.
There you go. So you can switch some heat to the edge now too to try to finish that up. Get it to fill in a little bit. Okay, I think that looks good. You can tell from my fiberglass that we are going to get purple color. Light purple. Great. So, overall, no one's bleeding, so it's a success.
Yet.
Yet. Yes. So what's going to happen next is these have to cool a bit before we can take a look at them. We're going to watch those 2 videos. That takes about 15-20 minutes. We'll then, while they're still hot, we can take some of the linear measurements. Once they cool down a little more, we'll move them over here to the light table. So we'll take the last sections off, but you can look at their coloration too. And we will also look for internal stress. You might not know this, but with cross polarizers, you can see internal stress. You ever heard this? Polarized light is an interesting thing. You see how that goes dark when I tilt it? So when you cross the polarizers, you can model it classically like the wave of the light, the electric vector is like shaking a string up and down. It's tied to a tree, a sine wave, yes, and it fits through slots in a picket fence vertically, but if I were to shake back and forth, they would be blocked and couldn't propagate through the fence. This is a classical mechanical model to describe what's going on, but it doesn't necessarily perfectly hold true. But if you cross the polarizers and then put a piece of glass in between, you can see any shift in polarization caused by the glass. And I don't know if you can see it, but I can see it. You see this rainbow striations of color The tightness of that pattern is directly proportional to how much internal stress there is in the glass. If you anneal the glass, it all goes to kind of like a gray color without these bands of color. But we'll be able to see lots of stress since this is surface quenched glass. I've also got some pieces of injection molded polystyrene, different shapes, forks and spoons and such, and little dishes. The cool thing about this is these also show preferred orientation. And you can see where it was injection molded. You can see the path that the polymer took if you know what you're looking for. So for both glass and plastic, simple cross polarizers are actually pretty instructive because you can see bonds that have preferred direction. Any preferred direction leads to internal stress. Like I just noticed this piece, be careful, has cracked. This is called spalling. And the edge fell off, and this would be like a razor blade. It'll probably start bleeding here. Yeah, so I sanded the edge. Those happen during the lab, and so you can actually file it, and it makes it not sharp. So I'll surface treat this one. But after the video, we'll move these over so you can see internal stress and all that. But first, let's take a look at some different aspects of glass making. The first one is a look inside a Dale Chihuly's hot shop. You may have ever heard of Dale Chihuly? No? Anybody ever been to a hot glass shop and seen people working with hot glass? A few?
Is that the same glass blowing?
Yes. So, I was at a shop in Corning, New York, and I got to see some people working in hot glass, freeform hot glass. It's pretty cool. Dale Chihuly is one of the most world-renowned glass artists. He's kind of an eccentric-looking fellow. He's got an eye patch that I used to think was from being poked with glass, but it's not. It was actually a result of a car accident. So I've come to respect him quite a bit. He really has a lot of installations worldwide, big museum pieces. He's an interesting fellow, you'll discover. So.
Well, his eye patch is from car accident. Seems likely for glass.
Right, I thought he would have poked his eye with some sharp glass like that, but no, it's less of an occupational hazard story.
Still glass. You know, maybe he picked up a quarter of those tails.
Yeah, maybe. Don't do it. All right, so let me test the sound here.
It's not working.
All right, Dale Chihuly. Now this is a little bit retro. This is probably late 90s. This is probably circa 1998. I think I was a junior in high school. That's a good year. But this is kind of a retro presentation of some of the people who work for Dale Chihuly and his shop in Seattle. We'll tell you all about it here momentarily.
Tell us where we are. Okay, we're at the Boathouse, Dale Chihuly's studio and home in Seattle, Washington. This is where Dale's work is made and where we conduct most of the business that he does. This is the hot shop where we have hot glass.
We first met Joe, who was telling us a little bit about why Seattle is so good for glass blowing, and it's because its climate is not too hot, not too cold.
Our glass is 2150 degrees Fahrenheit, and that's the working temperature of the glass. In order to melt it, we put it on what's called high fire, and it goes up to 2500 degrees to melt it. So we should take a trip to the furnace.
Okay.
That's
So a statement I never really expected to hear.
Oh no.
We're going to take a trip to the furnace.
Trip to the furnace.
So what are you doing now?
Well, I'm going to gather this, what we call a little gather here, and I'll You know, the pipe kind of heats up as we stick it in the furnace there. So we have this little device to keep ourselves from burning ourselves on the pipe. Turn, and then you kind of let it fall on center. There you go. It cools off.
Yeah.
There you go. See, natural. That's the right. Hang it down, and it'll go down.
Is the burn unit nearby?
We have a little device over there that catches us into the fire department. Kind of come out,
Yeah.
and then you lift it on out of there. Okay, up and out.
There you go. Keep turning.
Wow.
Good. Keep turning. Good. All right, now.
There you go. There you go. Now this is the marver. This is what we call the marver, and now you are marvering. Marvering the glass.
Marver's just heavy metal.
Yep. Very good. Oh, and this is a good shot coming up here too. With this is what we call a roller wrap.
We'll return to Foster in just a second. They're applying the red to it? Right.
Yeah. And these rollers are offset, so the bubble moves down and the color goes on.
It's like taffy.
Hale founded it.
Oh, he did?
Yeah. He was the founder of the school.
So is he like the main glass man in Seattle?
He's about the main glass man in the world.
Really?
Yeah.
I was going to school here at the University of Washington and was taking a degree in interior architecture. Started getting interested in glass, started melting glass, and one night I blew glass out of a little kiln. And then from there I decided I wanted to be a glass blower.
What we're working on today are these wall pieces, okay? And so what you see a dark bubble on the inside?
Yeah.
That's actually an air bubble with a thin layer of color. That's Bennett right there is about to drop on to the pipe. We're gonna just reheat it, shape it, and with my great team, we'll hopefully get it in the box.
So, just stay out of your way. Where should we be?
No, I don't want you to stay out of it. I want you to get right into it. I'm gonna actually have you help me a little bit here.
Martin works for me, but he also works on his own work and has his own exhibitions. And many of the glass blowers that have worked with me have gone on to develop their own careers. Some of them, like Martin's, stay around and still work for me. Others go out on their own entirely. But there are some, I don't know if anybody told you, but there's something like 50 glass shops now, glass furnace studios in the Seattle area.
It's not really glass blowing, it's more like glass shaping. Because there's a lot of prep work into shaping the bubble, and very little blowing.
Well, glass blowing is difficult to get started in because you have to have the equipment.
A little further.
So you've got an initial outlay of, a couple $100,000 just to have a small glass shop, and then to run it costs a couple $1,000 a day.
Actually, what you're gonna do is, these are wooden paddles, and they're to protect me from the heat.
Okay.
All right?
Teamwork. Hey.
You guys are awesome.
Oh, wow. I can't believe you can even talk.
Turn. Cap. Oh my gosh.
Should it be okay for you?
Wow. Blow? Yeah, shoot my chin. Stop blowing. All right, good. Level. Tip up. Right here. Don't stop on that.
This climate is conducive to glass blowing because it's not too hot. The only really bad climate for a glass blower is a hot one.
When you blow glass, you blow the bottom of the vessel first. And now we're going to break it off the blowpipe. Okay, cool. Glass always breaks at the coldest spot, right? So just little drop of water here, drop of water there.
Yes.
Boom.
Wow, there it is.
Is that cool?
What you saw down there was those.
See the color there? Any guesses on what the color is for the glass? I know we had really great success breaking that today, but I know what it is. That's manganese there in that glass. So we do have one piece of glass that is going to be pretty similar to that color. That's pretty much a straight manganese color. And the remelting they're doing, I think what we'll try to do for that one that broke, I should be able to remelt it. There's still plenty of heat in the furnace. These crucibles are supposedly able to deal with shock, thermal shock. So I'm thinking we'll probably just put those chunks back in the previous crucible, give it like 20 minutes, and it'll probably re-pour again. So we'll try that after this video. Worst case scenario, it blows up in my furnace, but I need to re-brick the inside anyway. So I don't think it'll happen either. I've done it before, so but we'll try that to fix the one that broke.
Techniques have been used for 2,000 years.
Squeeze it together so you get in. Good. Now push down. Okay. Good. Hit the lip pad with one paddle. Good, man. You are on the ball.
I'm just pushing down.
Push
I can't
harder.
even see
Push
it.
harder now. Ease into it. Push harder. Push. Let them open up. Good. Push, 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 push. All right. Now, when it starts to feel like it's not moving anymore, you're done. We've got as much work on that heat as we could. Now, come out. Good job. Whoa.
These were mine fire. And so with the...
Full heat. All right. I'll take those.
Okay.
So
How was that?
That was good. We got about 2 heats left.
Okay.
What we're doing now is we're going to peel this ball open flat to make the wall piece.
Quick word on what they're doing here. So we are quenching the glass. We're not annealing it. Because this is going to be whatever, put on a wall or a decoration or museum or something, whatever he's doing with these shapes. This has to be annealed. So they're going to put it into an annealing oven that's at, if this is melting at 1150, what ours is, we'd have to go down to like, 600 Celsius. I think they call it 800 Fahrenheit is what they've got theirs set to. But below the melting point, but above a softening point so that bonds that are trapped in a stretched position can break and reform with atoms that are closer to them. That relieves the internal stress. So they're going to now run and put this thing they just broke off the pipe into an annealing oven.
Alright, so these are coolers, Mark? Here, well, yeah, essentially they're ovens that are 900 degrees. The timing is just critical on that because you've got about, while it's heating, that all the work we're doing comes down to that very last heat. That's where the shape is made, that's where the beauty happens, that's where the nuance, the delicacy of the whole piece. All that work is just for that one heat. And then in a few seconds, you come over here, and if your timing's off, crash, it falls on the floor. Where do you get your inspiration from?
I'm lucky in that the ideas come to me. I probably don't run out of ideas. Sometimes you wonder if you run out of good ideas. Glass is a lot like water. There's a lot of, I like water, I like glass, I like ice. There's a lot of characteristics. And it also kind of works like the ocean, makes forms like this. There's some connection between all of that. Mm-hmm. So I end up blowing glass and stuff, everything. Half the stuff I make looks like it comes out of the ocean, mm-hmm. Even if you don't want it to. I like the rain. It's really, I find it conducive to thinking, and I always tell people, if you had to write a book, you want to go to the Caribbean to write the book, or you want to go to Ireland, which is a lot rainier than Seattle. And where they're going to write the best book, even most people admit it's going to probably be Ireland. Somebody is an aspiring glassblower, where do they want to go? They want to move to Seattle, because here we've got more glass activity than anywhere else. Venice has more glass factories and furnaces in Seattle, but we're second to Venice. And I think I would be proud to say that we probably have more glass artists.
Okay, so that is a nice view into art glass. There's plenty of videos I could show. What I like about this one is it's kind of like more informal, and it's more like a visit to this guy's place and not quite so sterile, maybe, a documentary. All right, so let's try to deal with our issue here. So that composition was P, right?
Yeah.
Right? Okay. I'm going to clean off the edge of this crucible a little bit. I can. Usually it's a little easier than that. Apparently that's not the crucible. Normally what happens when you break those off is it just sort of comes off the side very easily, like about like that. And you go like this a few times, and then it's a safe crucible to touch. That was like really on there. So what we'll do is pick a similar shade glass, like D1 from last time. That should be a more stable crucible than what I just did to that thing. We'll add these chunks to D1, and hopefully, I'll just leave it in that one. That looks even more similar. So we'll put these chunks in here, and then we will set that in the furnace and remelt it. And
Do you want me to grab the door?
what's that?
Do you want me to grab the door?
Sure, that would be great.
Let me know when you're ready.
Yep, I'm ready. So we're just going to set this to the side, and we will check back and see how that thing's doing in a little bit. And if we hear a big crash, I think we'll know what happened. But sometimes, you know, you just got to live on the edge. So next up, let's talk about the more industrial side of glass. In a normal semester, here's some more of Dale Chihuly's work. This guy's paid millions of dollars, him and his team, to put in installations like this. I believe there's one in Philadelphia Museum of Art. I had a student last semester that over the summer went to a museum. It was like, I wouldn't have known, but there was this huge glass display by Dale Chihuly, and he's like, wow, it was really awesome because he knew more of the backstory. Just imagine the time necessary to make that. It looks like, you know, a bunch of colorful eels, you know, crawling up that pole there.
Is that like a couple hundred individually?
Yeah,
pieces
those
or
are
just-
hundreds of individually blown and twisted bulbs of glass.
And how are they connected? It looks like there's some sort of central.
Yeah,
slot.
you know, it's not clear. I don't know if those are tied with really thin line or if there's some kind of a rigid support that they're threaded on, kind of like the drying rack. I don't know if there's like posts that those are fitting on. We'd have to investigate further because yeah, it looks like how's that connected? I don't know. But these are just a few. You could do a deep dive into his work and see all the crazy stuff that he's been able to pull off in his career. So anyway, let's talk about the glass bottle fabrication. But we normally go to Cardinal Glass in a given semester. Anybody ever been to Cardinal Glass? A few of us? For those of you who haven't, there's tours fairly often. I would go if you have an opportunity. We normally go in this class. It's not going to work out this semester just because there's still more limited mobility and touring and that kind of thing. But anyway, it's worth going to because you see an entire operation built around this material. They turn on that furnace and let it run for around 15 years before turning it off. Just, you know, think about that. It's Christmas Day. You're at home. Someone's there making glass. There's a blizzard. Everything's closed. Someone's there making glass. You can't turn it off because it's this room that's like 4 times the size of this room, full of glass being fired by natural gas, and it's really difficult to turn off. They rebuilt about 3 or 4 years ago, and they do have a way to drain it, and then you rebuild some of the brick, and then you refill it, but it's quite an undertaking. So this is a glass furnace similar to that, and that would be above all of the operation that you see here. There's a place where they're metering the glass out of this giant furnace, and you can actually cut it with metal pincers if it's the right viscosity and if it's the right coolant. There's some kind of a coolant that they're using that facilitates the process of cutting. And so then they use gravity. These pieces of glass are falling through dies that do some preliminary shaping as they fall downward through these dies. You'll see what I'm talking about. So then it goes to this thing called the scoot, and it looks like something out of Star Wars that then is moving these pieces of glass to bottle formers. There's a row of these at the bottom. Think about the split-second timing that the engineers had to come up with to make the maximum number of bottles. The glass has already started falling, and this is still working on the last bottle. It then closes the mold, and that next piece slams into that mold, falling from above. Split-second timing. I mean, when that goes wrong, this would be an absolute crazy madhouse with glass flying everywhere. I had a guy that said his dad worked as an electrical engineer at a place like this for a couple of weeks. He said that they didn't like turning off the line, and so they made them wire things while it was working. So he says he was, basically hugging one of these drop points, putting in a sensor, and the glass is flying right by his face. And so at lunchtime, he's asking the old timers, "How do you guys not get hurt?" And they're like, "Well, take a look at this." And they all had these horrifying burns all over them. So he decided that's probably not the job for him. But anyway, this is the industrial side of glass. A lot of the similar things apply: the temperature, annealing, the forming. The way this works, the glass goes into a pre-mold, and a little bubble is blown inside. It then gets moved to, it's called parison. It then gets moved to a larger blow mold where they then inflate that glass while it's still hot into that final bottle form. So just some things to watch out for as we roll through this one.
My job is to make college easier because students have a lot of fun.
After a word from our sponsor.
Glass is made of natural ingredients that are abundant. Making it uses less energy than producing metal or plastic, and it can be endlessly recycled. Whether they're coloured or clear then, glass bottles and jars are always green. The recipe for glass combines several natural raw materials. The main ones are silica sand, soda ash, and limestone. Silica sand usually makes up about 45% of the batch. The soda ash helps melt the silica evenly. It makes up about 15%. A limestone content of about 10% makes the finished glass more durable. These ingredients are combined with recycled glass called cullet. The factory's equipment feeds precise amounts of the materials into a furnace. After 24 hours at 1500 degrees Celsius, a gooey liquid that's the consistency of honey is produced. The molten glass pours out of the furnace. Shears cut the flow at precise intervals to produce cylindrical globs. Each glob is the exact amount required to make up one bottle or jar. They drop to a device called the scoop. The scoop moves them to troughs that feed them to jar forming and bottle forming machines. A glob of molten glass goes into a preliminary mold. Matter of seconds, it comes out as a miniature version of the bottle, known as a parison. Each parison then moves into a blow mold, the cavity of which is the shape of the final bottle. The equipment blows compressed air into the parison, stretching the glass outward towards the wall of the mold cavity. This process creates the final bottle shape and hollows out the inside. These are amber-coloured beer bottles. The colour is produced by adding small amounts of iron, sulphur and carbon to the glass mix.
Allegedly.
A similar manufacturing process is used to produce other types of bottles and jars. In this run, the company is making 375 milliliter wine bottles out of clear glass. This run is producing bottles also out of clear glass. This mold, though, has a special feature, a recessed insignia on one of the walls, which produces a raised insignia on the front of the bottle. After the bottles leave the forming machine, they travel through flames. Otherwise, they would cool down too quickly and crack from thermal shock. A loader now gently pushes the bottles into what's called an annealing layer. The bottles cool at a controlled rate as they move through the layer. This gradually releases the stress from the glass. As the bottles exit, they're sprayed with lubricant. This enables them to move smoothly through the rest of the inspection and packaging line. The bottles now single file to head into the automatic inspection station. As the machine spins each bottle, cameras and probes check for imperfections such as cracks or bubbles. The inspection equipment then examines the top to check dimensions and ensure the threads for the screw cap are molded correctly. Before shipping, each bottle gets a final visual inspection. The proportion of cullet in glass can be as high as 90%. Cullet melts at a lower temperature, so for every 10% of cullet in the mix, the factory uses up to 2.5% less energy to produce its glass. Now that is a clear incentive to recycle.
Hello, Twin Cities. We're
Alright, so we're pretty much done with the formality part here. Some things to keep in mind as you are, working through the lab. Let me pull up the specification sheet here. So remember that the terminology that's used in the lab is referring to a few different things. First of all, the glass former. The glass former is your base crystal structure that you are infusing with an ionic impurity. So that's silica. Sometimes you can use zinc oxide or lead oxide. We're not using lead oxide. Obviously, it's a little bit more hazardous during the manufacture, but you could. There's a flux. The sodium carbonate and calcium carbonate are serving as the flux. They do decompose thermally in the process. The carbonate turns into the oxide and CO2. And this decomposition is happening kind of as melting and dissolving the silica. So you get little bubbles. Calcium and magnesium are still acting as a flux, but because they have a +2 charge, they are also a stabilizer or strengthening agent. So they have two purposes. So calcium carbonate becoming calcium oxide is a stabilizer. Then we also have other modifiers in the glass, such as the metal oxide. Each glass has its own characteristic melt property. So, for instance, if you have a borate glass, it melts a little bit earlier. Now this axis is not for ours. We'd have to substitute in like, whatever, 1300, 1000, let's say 800, whatever. Let's say we match our our x-axis to the viscosity we observe. Every glass has a similar decrease in viscosity with temperature, and it would shift depending on the ingredients that are used. So borate shifts this down so that at 1150 we end up with an easy to melt glass. If we substituted potassium for sodium in our flux, it would shift this way and our viscosity would go up at our pour temperature of 1150. So this relationship is discussed in the procedure a bit. I also want to highlight one other thing to you, and that is on canvas. So if you go to Canvas and look at the file folder for this lab, there are some reference images that you'll need to answer a few questions. So those reference images are here under the heading Question Illustrations. So this illustrates a low, medium, and high viscosity. So we saw some examples that are not quite the full range, but encompassing some of that. This shows the role of flux loading. We didn't play around with that composition too much. We were just adding different ingredients, but this is showing how all other things held constant. If you decrease the flux, you increase the viscosity. An increased viscosity causes less spread on the steel plate, and so you get a smaller diameter as a result of the higher viscosity during pour, because less sodium carbonate flux was used. So we can see that kind of a trend. There's also the relationship between the flux that's used. We focused today on sodium flux, but you can use this diagram to answer the question of what would happen if we use lithium. Lithium is way more aggressive as a flux. It's because even though these are all +1 ions, lithium is so small, it's very effective at breaking those silicon-oxygen bonds. And so the same amount of lithium is way more potent and decreases your melt point. This one, of course, cracked, and I put it back together so we can take a picture of it. Sodium is probably the most well-behaved. But potassium, which is even bigger, +1, is less effective. And so we end up with a much smaller piece of glass for a similar batch recipe. We're just substituting in lithium for sodium, potassium. And we're normalizing based on the amount of moles present. So 0.46 moles present of the flux. So these images will help you out in determining those relationships for the questions in the lab. I think that's the technical presentation, let's say. So let's see where we're at, and if we can do some examination of the glass here yet. Those are still mildly painful. It's kind of hurt, but not too bad. So these are about ready. These will need a little more time. So what's probably going to happen, it's probably melted already, is we will probably let you take some measurements up here. Remember, please don't touch these crucibles, don't touch the fiberglass. But you can get some rulers and take some surface measurements. I'd like to have a little meeting with folks on the composition here to make sure that we've got these as good as we can before I scan them. And then I'll go scan these so we can all use them, and then I'll pass these back out to you. But go ahead and get away your goggles, because these still could shatter. But get the ruler, make some measurements. And if there was a question about the batch, come talk with me and we'll try to figure that out. Some of them kind of got a little out of shape.
Which one should you pick? An average of the two?
Right. I would pick just kind of like in between, like a
Thanks,
visual average. Yeah.
67 and a half.
So just trying to knock off the sharps here on this one.
Yeah.
These you can see that stress. That's why it cracked like that. It leaves stress when it cracks and splitting off those corners. Oh, what happened? Bubbles over.
Easiest scan out of the composition sheets and put like, so you can see it with this stuff. That'll be a good idea. Do it for this. So really all you do is the composition letter.
We can knock the temperature down on that.
Right more Jackson should have picture there so we do it too.
So, I'll be around till. Yeah, don't. We can take care of this later on or today. That's I guess an important outcome. So like could be products that well. This is perhaps 44. So it's a little bit high. Okay. All right. Well, we'll see if we can optimize all that. Okay, so for the batch that might have been less cobalt, is that plausible? Whoever that was. Maybe just take a look at which one that was. It was the second one with corn, right? It seemed like it had a lighter load. Yes, so L1 was 0.2 grams or 0.02 grams cobalt. M1 said it was 0.02, but I think it may have been less.
7.9.
Does that make sense? For the owners of M1? Yes, no, maybe. Who did M1?
That was us.
So can you guys measure that? Is it possible that it was a lower amount? 0.02 perhaps, or what? What do you think? For the cobalt. You're sure it's 0.02? So you're sure 0.02. So the difference is we didn't have sodium sulfate, otherwise it matches. But if you're sure that there wasn't any decimal error, then we will let that stand. Well, I trust you guys. All I'm saying is these things happen. Okay, so what was the other one that we were wondering about? The chrome finally turned.
I've got the questions done. No, I don't think
that's. Maybe I'll just go make that. Okay. No, it's certainly cobalt. It's just the 0.2 grams .02 is a really dark cobalt, and you can lighten it up by adding. So the ideal solution would have been if there was an extra decimal.
The last one.
0.02.
So basically, if we put in a whole bunch of water, got that close.
It was like.
So yours is
Like the different sizes.
you know, if for some reason there was like, yeah, if there was a lot sticking to the side, maybe, but if you pre-mixed it in the glass, it's probably weird. I'm not trying to make you guys, question your work or anything. It's just whenever it looks different, there's got to be some discrepancy. But sometimes we'd have to repeat it.
Excellent. So you guys just take
So
a bunch
it's
of
we'll just roll with it.
Yeah. You have them all.
Alright, so I will go make the scan of these. It's pretty toasty up there. So I will be right back.
How are we supposed to remember that? I guess it's bigger.
That one, I don't know how that one is shattering. That one didn't have an actual one that's shattered. Got shattered.
I guess that's, I mean, like, you got a picture of all of them together.
Yeah.
Some years.
Yeah, I just we don't.
Color observations.
Okay, so these batch records are scanned. I will be posting that online. So I'll come pick up your record for your lab report. So spread them out here a little bit. That way we can all look at the batch and compare what we end up with. Grab that for your group. Test our temperatures. Maybe we're ready to put them on the late people.
Do they all have a filter for that?
All of these do have sodium flux. We're making traditional soda lime glass. Soda. Was that one you flagged earlier? It'll be, so this is the danger of the bat.
That's this one's oh, okay.
So there's sodium flux and there's calcium flux.
Calcium?
It's a good time to look at the injection molded material.
Is that what it was? That help us? We use sodium. We use sodium. We did, yeah. We did pretty good.
That's his 6G.
Yeah, look at
Yeah.
There's no even one.
So let's put So what happens is it's showing you that there is a preferred direction for the bond that's not on the chain. So they're not all random. They're randomized. This gets randomized. There's no net. In fact, the light is propagating down a bonded direction. It ends up changing the light in a way that's going to pick up and essentially the speed of the light. Different colors have different speeds if they are going down a particular bond instead of a particular system. And so that overall effect of partial orientation has a translucent.
I think that's the same.
So
This for sure.
where was the injection?
Purified Silica for sure.
Based on orientation, there's my injection point, and it fills the mold
Not just the
here
brand.
over to here. Maybe I'm wrong. And here, this got injected here and filled all the way up to the points.
Use sodium carbonate and calcium carbonate.
Those dots are the ejector pin witness marks. So this is where the ejector closes, ejector plastic, hold. It opens up, and then there are ejector pins that push the piece of plastic out. Those are called ejector pin witness marks. And all injection mold plastic have that. So this one, interestingly, you can see those right there. You see that little defect.
No, I think what we gotta do is just look online at the scans.
Yeah.
Report all that.
This looks more like, I don't know what's going on here on the edge. There's something going on.
I'm not doing it right now, but I think that's what it is.
Something. Because that,
I mean, we don't even have glass. So we don't even have our glass.
Is that what you guys are waiting for?
I don't know really.
you can learn a lot.
It's tough, right?
I don't think that's
So we're gonna get some light behind him now on the leg table. So there's something even better what's going on.
Yeah.
Can shatter still in your hands, so don't squeeze them tightly.
Yeah, I've been busy too, but I've been
Random here. So now one more try to Dave, second time around. Quite tame. I noticed that
You got it there.
Sure. Yeah. Kind of like paint, but not quite. More like. So, there's your stress field. Sometimes you'll see bubble effects. You can see that the stress lines are sometimes curved through them. We did have the one crack while on here, and the student that was looking at the time the color change. Pretty interesting. Yeah, you just relieve the stress instead of this curving through. If you see an area with really tight bands of color, it's more likely that that's going to fall on the side. This one had a weird fall pattern, and compare that one, and you can see that the symmetric pattern then kind of deviates up into that crack zone, and makes this a perfect example of glass. If you compare this with like heated glass is kind of cool, and it's just great. You don't see any color in it. So anyway, take a look at that, and I'll see if I can't prep this for the final four, assuming it's ready. Yeah, a little fiberglass action there. So I think we'll try this last pour. So if we want to revise our rolls here, or if you're dying to try one of these rolls, you can try it again here. But we'll need somebody to torch here. So you're ready.
Yep. I can get it.
Anybody want to torch? Yeah, right.
I'll yell fire.
This one is P1, right?
Yeah.
Maybe try.
You want to stamp it still?
Yeah, let's go ahead. So just set those up so it's backward 1 P when you're looking at it from the top, and then it'll be P1.
There.
All right, so let's try this final guy here. This is the repour, yes. I'm a little bit concerned since we use a different glass in the crucible that we could get a. Okay, I think that's good. I think that one's better. Go ahead and stamp it. I think we're good. The one thing I'm concerned about is this was a slightly different composition. And they didn't give it an enormous amount of time for those two compositions to mix. So it's possible to be bands of one glass in another glass, which can also lead to cracking. But we'll see.
Oh.
At least it doesn't have a crucible sticking to it. For now.
Is that crucible crap?
It doesn't look like that top edge is a bit iffy. So, in theory, you can get multiple cycles with these crucibles. Sometimes these are only a single cycle because each composition is a little different. So we buy those by the gross, and they're a few dollars maybe, or $1 per crucible or more, depends on who we get them from. So they're not so expensive that you feel obligated to use them more than once, but I'd like to whenever I can, because if the color's the same, it could be reused.
You're also the type of guy you think of a quarter when the guy
Yeah.
explicitly tells you not to.
That's the kind of guy I am, yeah. Don't do it. It was funny.
Bad luck.
I am too.
Well, I think you've got your knowledge on that one today.
Yeah.
Should take a picture of all of them.
Get that up.
So the stabilizer would be the calcium. Calcium sensors is both the This is weight that works great industrially on a large scale, but I'm still deciding if it really seems to be working for us
You want to do it?
on a small scale. But we've got the base, the main flux, the sodium flux, secondary flux and strengthener, the calcium ion, color modifiers, whatever we put here. The borate would be considered modifier as well. Well, it's an alternate source base material, but this one dramatically lowers the voltage. So that one is technically still a base crystal, but I kind of do purpose that as sort of an alternate. So that's the way I would classify these very
First one?
I know, that's a common one.
That's Ed.
Plus calcium plus iron.
Oh,
So it is going on two oxides at the same time. Where sodium more yeah, it does. One of its bonds is still to silicon, the other being one minus charge. It's a partial exposed oxide. One's going on the oxide. Sodium caps that, they can slide past and it doesn't maintain strength. Calcium still bridges one octane calcium and that makes it worse constantly. Aluminum, 3+, it's even more. It's so aggressive in its kind of like holding together ability. It's not really even considered a plus. It's more of a special. Somewhere you can hold on to 3 oxides at once, and then you really have a big increase in strength.
I'll give it back.
I have done some alumina. If you look at some of the historic compositions here listed, there's one in particular.
We do need to measure.
Yeah, that's weird. It's like dark, it's the weird.
So this is
I don't know how to describe it.
Heat.
Yeah. Silicate glass. This one's kind of similar.
You guys describe this thing.
Because it has a really high amount of borate.
The guy's got a great
And it's got
Oh, great.
aluminum.
There we
So,
go. That's
this one in particular,
What is
Did you give us the chemical?
I give that sucker a 754.
yeah, this is on the original document. So these are the base compositions.
It's
Mostly
mostly-
sort of your,
You can also say that when it's shattered.
we don't use
He was
like glass.
Use it.
Your glass.
And the one that curves is-
So it works.
Hasn't shared
What
yet.
about the ions?
Before, so I don't know how to mark it down.
Oh, I said
But
yes.
this is just asking me.
It's the only one.
It's really the identity of the flux. So in this case, it's kind of boring.
That was
It's
more
all-
about,
so
it didn't shatter, it's not
those
here.
comparison images let you see.
It more
like,
broke
other
than it was
fluxes.
shattered.
But it did shatter.
Because of the borates that we had some, that would be the main difference in Scotland itself. Higher borate really spread out low viscosity glass versus
Wait, this was pure.
Yeah.
How do you have?
assuming similar recovery from the crucible.
Yeah.
That's 67. Okay, that makes more sense. 61. So those would be the higher viscosity and the lower viscosity that pours easily. That one was spread. Yeah, for the ion, what you're doing is kind of compare to this. Whenever we're adding chrome, that's chrome 3+. When we're adding iron, it's usually iron 2 or iron 3. So I would look at the degrees that were added. And so, let's say it was copper oxide, Cu. That's a copper 2 oxide. So the copper 2 ion would be your ion. So Cu. And for concentration, I'm going to try to distill down our batch records into a spreadsheet they've got me here. And so what you end up doing is calculating the mass of the metal itself in the oxide. So let's say it was 1 gram of metal oxide, and after looking at the formula, you determine that it's 67% metal and the remainder is oxide. So you would take the amount that you added, 1 gram, that times 0.67, 67%. So that's 0.67 grams. Then you divide that by the total batch weight. Total batch weight, you take all the ingredients and add it together. 0.67 divided by 150 grams times 100%. So you can see some of them calculated out here. 1.05% cobalt, 1% copper 2+. No, in some cases there was more than one. So you would have to add like copper or 1% copper and 0.05% chrome. A few of them were too. So you could just add comma and put together for that.
I want 73.
Yeah, and so I'll try to get that prepared and out to the group well before it's due. Yeah, so I'll be posting, especially for that concentration, I'll be posting the batch records in hopefully a spreadsheet. Cut down on time. Yeah, sure. And that's posted too, but obviously feel free to. It should be, but you might want to take a picture just in case. But it should be. So from the video that'll be posted, and I'll put down the playlist, you could assess how quickly it poured out. From the diameter, you're looking at a small diameter that correlates to a high viscosity, a large diameter that correlates to a low viscosity, but it pours easily. So you can extrapolate that from your measurements. If you do it semi-quantitatively, you say low, medium, high, you can rate it from 1 to 10. It's kind of up to you. Right. So specifically that A rating, let me pull out that sample here. I totally should have mentioned that earlier, but this is the A batch. That's the standard silica that for some reason this year looks like a little impure. That's from previous years, so it's blue. But this is considered yellowish average.
It's very light yellow.
It's all probably. Try that out. So if we then benchmark yours against that, so
Let's do plus,
yeah, you can do a deviation. Since it's semi-quantitative, we're not really changing it to the employee's value or the viscosity during the board. We're just kind of assessing it. So roughly.
no, that one, Q1.
Yeah.
Did we say that did correct or no? The reason why I correct took a wrench.
It did not crack by itself, so that's not really the glass's fault. So far it's still pretty stable. So yeah, it could be a no.
None of them cracked.
Yeah, so far they're stable. We used to have about 2 or 3 crack every time we did this, but I tried to optimize them for them to be more stable. Potassium glass at 1150 dark we stabilize it. It really needs to get poured around 13. But since we're making it part of the experiment, it's pouring at 1150 and seeing what we end up with. That's why we're using sodium. I used to do lithium as well, but that's so aggressive it started to soften the inside of the furnace. So you'll notice that the top element has sagged quite a bit, and that's likely accelerated by the fact that we used to do lithium glass, and those lithium ions have evaporated, impregnated that wall, and it starts to sag.
That's what gives you the color.
Yellow.
The iron, the ion is what's responsible for color. Yeah, basically. So you can actually calculate that from the formula. So if it is copper oxide, that's copper 2 plus. If it's Fe2O3, that's iron 3. At least it's started off as iron. Oxidation states can't change the glass. So I just go with one that starts off being. This is cobalt 2 plus and chrome 3 plus. So just work off your batch right there. So the weight percent is you figure out how much of the oxide is copper. So let's say it's 80%. So if we had 2 grams, you take 0.8 times 2, and that gives you your copper mass. You then divide that by the total batch, which is around 150. Let's see. then multiply by 100%, and then this would give us about 1% copper in this container. So I'm going to take all of your batch records and try to transpose that to a spreadsheet. Or I will at least put them up there with a spreadsheet that you can transpose. See how much time I have. Yeah, and then you just put in all those values and it calculates the amount of the metal divided by the batch weight. And I'm going to give 1%. So the velocity rate. Viscosity. Yeah, that is what's being referred to. And so this was a pretty average batch without any extra impurities or stuff added to it. So this is probably medium diameter, medium viscosity. Yeah, to benchmark everything else.
Just along the size or the look?
Probably the size, but the videos will also be posted so you can actually tell based on the thickness of the glass when it pours out.
Oh, yeah.
That actually is a pretty good indicator as well. Probably the diameter is the one that's easiest since that's the part number that we're getting. But it should match up with the qualitative assessment rate. Right, that's what you do here. This is batch A, so it's somewhere around 72 or something.
The other.
So usually millimeters, you're probably reporting in centimeters. I think it's around 72 millimeters.
75.
If, however you're citing it, I would just keep it the same. I mean, I'd probably call that 73 or 74 at that point for arm wrestling over pretty small amounts.
Right.
Yeah, just the diameter measurements is a good way to do it. Now there is an assumption there. The assumption is I'm pouring them at the same angle for about the same amount of time and they're at approximately the same temperature. But if we assume all those are correct, it's actually pretty good.
Yeah, like that, or like we just make up the diameter.
Lower viscosity. I just forgot that. Water is a fairly low viscosity and we pour all over. So the higher the viscosity, the more it stands up. This flow during the pour, the smaller the diameter will be. So it's an inverse relationship. Yeah. So, you know, this would be medium, this would be a higher viscosity, this is pretty much medium, this is a lower viscosity, so this is a little bit lower. Pretty much you can do it that way, or you could try to go 1 through 10, or some people were saying, I'm going to do a delta value, and I'm going to show that this one deviates 5 millimeters lower, and so I'm happy to accommodate your qualitative or semi-quantitative method. Because there are various ways. The best way would be to somehow actually get a viscosity unit measurement. That's kind of tricky for the amount of glass that we're making. It can be done. You know, you can imagine having a hot crucible and rotating material and torque necessary to turn it.
You want to keep that or?
There's various ways you can do it. But
I don't really care. They're scanned anyways.
Yeah.
Yeah. I mostly just want us to think about the viscosity difference.
You have to say it. I have everything I need. Yeah, it's all that is just answering those kind of questions.
Okay.
So, do you have a full card left?
Yeah, mine's got a couple of written on now.
Still
Yeah,
close.
Did you?
Yeah. So,
Did you have time to post for the rest of everybody?
I got it scanned. I'll be putting that into the folder hopefully still today. And I'll try to get out my closest spreadsheet and see how, see if I can just transpose that data. I think it was, as far as the color goes, First time we tried it, I think we may have heated it longer than, so it might have at one point had the right concentration to be brown, but no longer. So it just needs to get optimized, I guess. So we'll probably try by increasing the loading. Some references say the loading iron is necessary too, and so we may have had too pure, since we opted for the pure silica, pure ingredients. The bottle manufacturer may be assuming you're using a sand source that has a little bit of iron pure. So it could very well be there's not enough iron to see that color. So the next move would probably be to get a little iron doped in, and then maybe increase by 3 or 5 fold the amount you put in. See if you get this color. So you think? Great. But it's an experiment. Who knows? There's also some furnaces that, because they use natural gas, it's a more reducing flame. And so then it tends to have lower oxidation numbers. This is an electric furnace in air, is supplying lots of oxygen, and so it likely moves to a higher oxidation number, and that dramatically changes the color. And so the fact that we are in oxidative environment, sometimes I have to play around with that. You can compensate for that by adding charcoal or cream of tartar, believe it or not, is one thing they add to add a carbon source that then can supply extra electrons during the firing process and keep your oxidation numbers lower in your metal. So there's different methods, so we'll probably just try to optimize. I'd like to have the sulfur carbon color, but not this year. Yeah.
So for when I compare the diameters,
Yes.
the viscosity, is there a certain range that I should call medium viscosity or whatever?
I just went with 70 low, 75 medium, 80 high.
Yeah, I think that's
probably
fine.
I made 68.
Yeah, these are, I don't necessarily have an exact range in mind. I'm wanting you to assess, and as long as you don't have it inverted. You were saying that the biggest ones have a high viscosity, the smallest ones have a low viscosity. I think clearly that's something to be corrected. But your characterization method is okay. I'll roll with whatever you come up with.
There's only one.
That one with the double boring was like
Priority registration?
Yeah, way beyond
Yeah,
my
next year we'll
expectations.
get priority.
So as soon as I poured it and I saw how quickly it exited, I'm like, holy cow, what happened?
Right after one.
My bad.
But then, especially because it didn't even mention borate, and so I'm like, what is going on? You're
Yeah,
like,
no,
"Oh."
our sheet was an absolute mess because we were just like, I was like flying blind basically because I was fogging up really bad.
Sure.
I got bring by some stuff about
Yeah, absolutely.
So I was thinking, we were talking about getting every solution that came across was an absolute nightmare. I ended up like actually just like taking apart an old refrigerator, maybe close around that. What I ended up coming across at one point was doing a dry cell, which does the same which does create that piping downstream mix.
Yeah.
But I was thinking about if I ran it through a bubbler, just being under so it pumps water out underneath water. If there were flashback and I found towards the head of flashback, it would keep it as that. And on top of that, so I've been working on SolidWorks.
Yeah.
So I was doing a design for it. Yeah. So this is kind of like the start of the cell. I do need to fix these plates. They're kind of, the directions on there are a little screwed up.
Okay.
But here's kind of what I was thinking with the bubbler. So that it doesn't, so the thing doesn't actually explode in the flashback.
Because you're limiting the amount in that secondary reservoir, you're probably going to be in pretty good shape.
Yeah.
You just want to eliminate the possibility of your storage chamber igniting.
And then what I did on top of that, just so that if it does go back into this thing and it does pop, I have this little kind of pop valve looking thing here.
Right, but
That
it's
if
like,
I'd have a spring here that puts down, but if it did blow out, it would.
Right, and so
yeah, this
one
part
thing
would, like,
that you might benefit from is increasing the diameter it is. Because depending on how much headspace there was, it might just pop that cap off. But if you had more venting in a larger button, then there would be no impetus for it to do that because the whole thing would just reset. And so if it's just as easy to make a larger sealing surface and to increase the size of those vents, if you're making like a seal on this outer rim, then
I got like a little gasket in there.
Yeah, I think I'd probably
increase the diameter. That wouldn't be hard to do, I don't think. Because like I said, I got access to the machining lab, so this would actually be like an aluminum piece.
Okay.
That I can work on the lathe and the mill to whatever dimensions work best for me. Only thing, it just means I think I would probably change up how this thing is designed a little bit.
So can that be plastic?
It could be plastic, I suppose.
So one other thing to keep in mind as a design principle is for things that hold potentially explosive things like this, you want to minimize acceleratable mass.
Okay.
So in other words, having a low density plastic is less of a hazard than having a high density metal.
Only reason I had this one as aluminum was just because it's what's in the machining lab, and also
and
I just was
may be
if
okay.
if it did burst, I was just thinking, stronger, and it's no chance of like melting.
Well, what is this material?
This is acrylic.
So it is acrylic.
Yes.
Okay. So if this is acrylic, then your blowout's going to occur here.
Yeah.
And it wouldn't fragment the aluminum.
Yeah.
Because you want to eliminate the possibility of fragmentation of that material. So if this is your weak link, I don't think you'd have to worry as much here. But if this whole thing was an aluminum enclosure,
yeah, I don't know.
I'd have to think about that.
So this is just PVC. This would just be PVC. It was just the only reason this top part is aluminum is because that's what's usually being worked with in the machining lab. But if I could, that just means I could probably buy a block of plastic or something and work on that.
If this is acrylic and PVC, you're probably okay because this top part would be stable and it would the force would go down in the opposite direction probably.
Yeah. And I mean, the whole point is that this thing would keep it from bursting.
Hopefully,
so yeah.
I'm just thinking through contingencies.
Yeah.
And so whenever I'm working with demos that involve rapid expansion, I'm always trying to reduce acceleratable mass because if you get hit by like high velocity plastic, it does way less damage than high velocity plastic.
Yeah, for sure.
But aluminum is also pretty lightweight.
And it's not very brittle either.
Yeah. So you're probably okay.
Yeah, sweet. Yeah, I just want like I said, I was looking at all these ways to like build compressors and repurpose things into compressors, and on top of it all being just a nightmare to do, it was also now I'm dealing with compressed hydrogen, and, which is just like I said, absolutely.
You also have to have like sealed motors or separate motors so that there's no sparks. Since those are often brush-driven motors, that can ignite it and just.
And that's what a lot of those things. That's what a lot of those like videos and like articles and everything I was reading were all saying. How risky it all was. I'm just sitting there. I'm like, there's got to be a better way. So on top of not doing like the wet cell version, with the two.
Yeah, I think that getting away from mechanical compressor is a good idea.
Yeah.
I think that there's still potential for this water bladder idea because you could compress it using a non-mechanical means. But anything that's like a motor-driven mechanical pump is probably a bad idea.
Not this one.
Yeah, I was just like I said, I just want
Now, you saw the schematic or the examples I gave you of commercially available software, right?
Oh, I forgot about those.
So I did not dig fully into.
I did look at like a bunch of them, just like because I ended up doing that kind of research too.
Well, you can see how they fit all these things in a fairly small footprint, and so clearly they're working on solving these same problems.
Yeah.
So I thought that by looking at some of those, you might get some design constraint ideas.
Yeah, I did end up. I've been comparing with ones that I've seen on YouTube and stuff like that. But yeah, I did forget.
It's just worth maybe taking a second look at.
I'll definitely do that. Yeah. This SolidWorks models has been the stuff I've been working on like the last 2 days.
Yeah, sure.
But yeah, I got that, and then I don't have like the actual tank.
But I think as long as you're not wanting to make a large reservoir,
Yeah.
then by limiting the amount of hydrogen present, you're making it safe.
Mm-hmm.
Like, what is the maximum size of your containment?
So this is it.
Or are you going to be using it as you make it?
It would be using as I make it.
That's the way to
so
go.
it's just like it literally, it just feeds right through and then.
Right.
So this is like the basically just like a reservoir for the electrolyte.
Mm-hmm.
And it pumps through. And
So I would try to come up with what you consider to be your total gas volume.
that's actually luckily the SolidWorks has like an evaluate.
Okay.
So I can.
Would there be a pressure sensor that turns this thing off if you get to a certain pressure inside, or how are you? What's the
That's literally that's the next thing I want to work on is maybe putting a pressure gauge on here.
Because it could turn off the circuit if it got to a certain point.
Yeah, that is the next like step for me is trying to figure that out. Yeah, first I wanted to figure out make sure I'm not building basically a small frag grenade.
Exactly.
And then after that is making it safer, and then actually being able to pump out the PSI. The only thing right now I'm kind of wondering is if you think, in your personal opinion, this would be there's a bunch of neutral plates running in here. This is roughly 4 inches wide. Dimension wise, all the neutral plates in here are 10 by 12 inches.
Okay.
So I think I've got, I want to say 22 in here right now. Do you think around that amount would be enough to produce enough hydrogen? Because I can really easily add more. I actually found out, so I was working on like, how am I going to do these materials? And I talked to the guy in charge, Paul Craig, he's in charge of like the purchasing for all the labs. And he's like, we have a bunch of leftover steel sheets from when we redid Frickland like 30 years ago, and they have a ridiculous stack of sheets. So I have basically all the steel I could possibly use.
Well, so I'm going to try to. So what's the geometry of this inside?
Internally,
because one thing that you're not accounting for yet is heating. And so the more layers you put in, the more heat you're going to be pumping out.
Okay.
So there's going to be a need to heat sink this.
Okay.
Otherwise, you can get into some trouble.
So when you say geometry, you mean like the volume on the inside, or?
I'm just wondering about the total electrolyte volume and the total desired output gas volume that you would say is like your maximum.
Yeah, I got to figure out like, I got to look into the specs of the little like jeweler's torch I was looking at.
Okay.
To figure out what PSI is required for it.
Well, and this is essentially parallel plates with spacers, and you're going to electrify them alternately with a direct current. Is that what's your wiring?
So these plates, the anode, and these are like mixed up on the what side they're on.
Okay.
But basically, there would be on this side, kind of looking like this. There would be one, like these two plates would be connected. I saw a little copper rod almost that I would run through this.
Yeah.
I saw, and then so I'd have one side be anode, one side be cathode.
But then, what are the other interleaves there? Because if I see you've got 3 taps here and 2 taps over there.
Yeah, that's where it's screwed up. It should be 2 on each side. This was just messed up because I wasn't really thinking at the time.
Well, why are there more additional layers? So
what is this?
Right.
These are rubber gaskets.
So what is this white?
These are neutral plates. These are stainless steel plates.
Now, what do you mean by neutral plates?
Just not attached to any electricity. Basically, the guy, like the videos I was watching, made it seem like the solution would almost act as a conductor on the inside as well, so it's almost like spreading out the voltage. But I was also kind of confused by that, so I was also possibly planning on like having just the plates all these plates be connected by something similar to this, just lower.
So I'd have to see. the rationale of what they're saying, because that. Are they using a neutral plate to make a channel that it causes a further path length
It's
between
this guy explains it as almost spreading out the voltage, almost. Like that's just the term he uses. He's not. This dude's no professional.
Okay.
So this is a very, very condensed and simplified version of it, but this is basically exactly how it works. So these big lines are our anodes and cathodes. The little lines are neutral plates. The empty spaces are the gaskets, but we don't really need to show that in order to show how it works. And these big tubes here are the in and outs. So this top one is the out, where our gas comes out of, which is oxygen and hydrogen, and the bottom one is the input, which we pump water into. So our cell works by having electricity run through the cell, splitting the water into hydrogen and oxygen. Now, the electricity wants to jump from the negative plate to the positive plate, right? But because we have our neutral plates in between, the neutral plates divide the original voltage into however many you're dividing by. So we have 5 neutral plates in between, which means if we have 12 volts, we divide it by 5. That is a 5, in fact, and that'll give us 2.4 volts, right? So each of these spaces here, right, in between, has, if you measure from this plate to this plate, the gap in between here is going to measure 2.4 volts.
The way I understand it is he's talking about as the voltage goes through like the electrolyte solution between the plates. Right. I'm wondering if that is the heat sink solution.
True for the other ones here. So
I don't really.
Have our current jumping from.
Yeah, I have to think more about this claim, because
each time it does that.
The only in every single one of the dry cell generators I've looked at, like this guy, they all have space, and so this is the one that like this guy, it doesn't do like a description. He's just showing him building it, but it's the same situation. So for him, he's got one big anode, one big cathode, and then a bunch of neutral plates in the center.
So how does the electrolyte get into the internal chamber?
So
between each one?
So if you see here,
there's holes drilled in the plates?
Yeah, so if you look at mine here, I would have my tank attached to this over here, and so input, it would be going in here and here from the side, and then hoses attached to the top here, pumping out basically the hydrogen oxygen mix and like the foam from the solution. So back into the one reservoir.
Each plate has holes drilled across the top and bottom for solution in the bottom.
Yes. It's just there's 2 holes on the anode cathode, so it flows evenly throughout the entire thing. Same with an additional hole up here that's not on the outer plates.
So if you just have a higher voltage I'm going to have to look up a couple things on that, because
I actually have honors colloquium starting in a few minutes here, so I got to run over the MSc.
We can go through this later.
Yeah, is it? Let's see, I'm just trying to. Yeah, if we want to talk. We could either talk during like an online office hours, or if you wanted to
have a special meeting for it to be fine.
Yeah, that too. Because I have a lot of the stuff I kind of got to show you in person, but I know Stout doesn't want to do in-person office hours. If you wanted at some point, like I work over at Ted's. I have an employee discount sometime after work one of these days. I could meet you over there. My treat for helping me out.
Yeah, we could try something like that, or we could come over here and work in the lab. It's also fine.
All right, I'll get that figured. Like I said, I gotta run because I gotta run over to the MSc.
Sounds good. We'll see you later.
Yeah, I'll get that. I'll once probably tomorrow, because I got a lot of stuff I gotta get done tonight. I'll shoot you an email and once I figure out like my availability and everything.
Yeah, that'd be perfect. And like I said, the way that everyone seems to be doing the same thing, there must be something to that that's the best mode. But something's not completely making sense to me.
My guess is like the reason for it is that the voltage like with the solution,
Mm-hmm.
and I'm thinking that it's a heat sink thing that keeps each plate from getting ridiculously hot and possibly melting the gaskets.
Okay.
That was just kind of my, like, I didn't really question because literally every single one of the dry cell generators I've
Yeah,
like
they
had
all
one
have
like
the
that.
same, yeah. Okay.
So that's just kind of that was just kind of my assumption at the time.
Great.
Yeah. All right. Well,
Good.
once again, thanks for the help.
Yeah,
I'll
no
see you
problem.
around.
See you later.